Let me tell you a little bit about communication satellites, guys. So we talked about twisted pair and we talked about fiber optic cables. Twisted pair is a metallic wire, pair of wires, so they're twisted around one another and they carry electric signal. Why are they twisted? Anybody knows the reason for twisting the twisted pair?
Because to try to avoid the received signals of radio.
Okay, so to reduce the effect of taking noise, taking electromagnetic radiation and generating an electric signal inside it that we consider noise. Fiber optic cable does not get affected by electromagnetic noise, and it doesn't generate magnetic noise either. All right, both wires, even though they're used to connect networks, local area networks, and sometimes even long distance networks, in the case of fiber optic, but they're both still cables. And cables have this property, that's what they're made of, to take the signal or information from one point to another point. They're point to point. They're not broadcast. You need to be connected to a wire if the network only works on wires. So all fiber optic cables, all cables are considered to be point to point. If you need to connect one point to another point, they're a very good idea. But they're not good for broadcasting, or broadcasting will always be limited. How many devices you have physically connected on those cables that you can broadcast the information to. But they're not like radio transmitters or satellites that can transmit to an entire city. And that's the next media or medium that we'll talk about, and that's communication satellites. And communication satellites, like transmitters, like radio transmitters. A radio transmitter, maybe the transmitter in a city, in an area in a city, will start transmitting the signal to everybody in that area, within a certain range of that area. So satellites are placed in the space around Earth. Like a satellite would be a certain distance from Earth, and it's spinning around Earth continuously in the same orbit. And there are thousands of satellites orbiting around Earth. And the idea in a satellite, first, all communication satellites, there are other satellites that are not communication satellites, but all the satellites we will deal with that are associated with communication systems are all around the equator of Earth. So if Earth is around it and that equator is there, the circle, all satellites are on a circle that's just bigger, but they are around the equator. They don't rotate around Earth, pole to pole, around the pole or any other angle, only at the equator. So looking down at Earth, if this was the North Pole and down at the bottom pole, then there you'll see a big circle with all the satellites around it. And they're all spinning at tremendous speed. And the speed they rotate at, we're not measuring it in how many kilometers per hour, because if you were on Earth at the equator, and if there was a bridge or a road around Earth, and if you drive a car or an airplane at the speed of 1,000 kilometers, you probably go around the equator in 24 hours. The equator is approximately 24,000 kilometers. So if you are spinning, driving really fast or flying real fast on the surface of Earth at the equator, it takes you 24 hours to rotate. But of course, the bigger the circle, the longer the distance that you'll have to cover to travel around Earth. But all satellites rotate around Earth, again, once every 24 hours. And the way satellites work usually, for example, we have a television station here that sends one signal to this satellite. And a satellite has two devices. It's a receiver and a transmitter, immediate. It's like an amplifier, it's like a repeater. It takes a signal, generates another signal, and sends it. But this one will send it in the opposite direction. So the signal goes up to the satellite, and the satellite will send it back, but it will cover large surface of the Earth. It can be as large as the continent of Europe, covered by one satellite, one transmission. So that's how good satellites are in broadcasting. They can broadcast to a city. Like if you want to broadcast to the city of London, if you have something to transmit to a city of London, imagine you say, okay, do you want to use satellite or you want to use fiber optic cable? Then you have to start installing fiber optic cable. It will probably take you 20 years to do so. A satellite, there are hundreds or thousands of satellites up there, and they're available. And it's a service available to anybody. If you want to transmit tomorrow for 2 hours to the people of South Africa or people of, Sydney, all you have to do is call, find a company that has the satellite, say, I need transmission tomorrow for 2 hours. They'll probably tell you it's $18,000. If you have the card, you have it. You can transmit computer signal, you can transmit radio signal, TV, whatever you want. It's available. So the availability is there. And that's one major advantage of satellites. If you want to start transmitting and you say, all right, we're going to go into the Sahara and we're going to need a network. Let's send somebody to start building the network. It'll take you 6 months to build a huge network somewhere in the Sahara. It'll take you 24 hours to do it by a satellite. So if you're looking for quick setup, satellite has the biggest advantage. It's available. You can transmit it to a city, to a country, to a continent, as much as you want. And so the area, so that's what a satellite is. That's a device that's floating up in the air. It's like radio signals on Earth, how it started. On Earth, if you have a radio station here, like RTE, and it transmits, and the signal goes around only, say, for about 40 kilometers, for example. So if somebody else lives at a distance of 60 kilometers, you want to cover the whole of Ireland, then you need another repeater somewhere here that receives this signal and transmits it again for another 60 kilometers or 100 kilometers. This is radio transmission now. It's wireless. You broadcast it. You can broadcast it to a big area. You can limit it to smallish area as well. And that's how all radio stations on Earth work. After certain distance, as long as the signal is still receivable, you have a receiver from one end and a transmitter to the other end. And same with this one, a receiver, transmitter, and you install a few of them and you can cover the country. So that's, instead of having a receiver transmitter on the surface of Earth, they said, okay, let's have it in space. So now we have it in space. Now, and if you want to receive your television signal and you're sitting here at home, you need a special antenna that can receive the signal from satellites. And there are many different types. So the famous one is the dish, the satellite dish, they call it. So you have a dish that you point it at that satellite. It needs to be pointing exactly at that satellite. If it's 1 degree out, it will still work. But 2 degrees, probably you start getting bad signal. 3 degrees, you're out of range. You can't. So you need to really be aiming at that satellite. And you can change it. You can aim it at another satellite. And most dish receivers, they have an electric motor. So from the controller you have sitting beside the television, if you want to go to that satellite, the motor knows, oh, it's at a different angle, so it will rotate it that way automatically on your behalf. Otherwise, you have a fixed 1-to-1 satellite. So you can, on one satellite, you can probably watch 50 TV channels, but if you have that dish motor that can be moved, you can aim at any of the other satellites. You can watch thousands of television stations if you have the time, and all the languages. And you can put up with all the mess that's there. But anyway, that's how satellite works. Now remember, you're pointing at that satellite, but Earth is spinning at around, you are sitting, but you and your sitting room are moving at about 1,000 kilometers an hour. Right now, we're all moving, but we're just so used to it, we feel they're fixed. It doesn't matter. The satellite is there, but you rotate, then you're no longer pointing to the satellite. No, the satellite is actually moving with us exactly at the same rotational speed. So if my dish is pointing at this satellite and I rotate, the satellite rotates with me. So it's moving like that all the time. Of course, it's spinning, it's going at much faster distance speed, longitudinal speed. But at rotational speed, we're going exactly at the same angular speed. We finish the revolution every 24 hours. So the satellite to us is relatively fixed. And that's the greatest thing, is that it's fixed to us. So we're always receiving the signal. We don't have to keep adjusting every day. And that's why satellites have to be put at a certain distance from Earth. And once they're put there, they never, well, they don't seem to change. They go around because there's no air there, there's no resistance. They don't have engine that keeps pushing them forward. It's space. And I don't know, the third law of motion says a motion or a body in motion will continue in that motion unless affected upon by another force. So there's no air to resist it, so it will continue at the same speed. So when a satellite is launched, they usually are launched from a location somewhere around the equator. So, you know, the moment they leave Earth and they go to tremendous speed with that rocket. And then when there's space, the rocket stops and the satellite just keeps going at that speed. So it's measured a certain speed and even the angle. So if we're on the North Pole and we release the rocket, it will be rotating, you know, around that won't work. So all communication satellites that we release, they are actually released right at the equator, and they continue in that orbit. Once they are placed into orbit, how do they stay in that orbit? And every satellite that rotates, there are actually two forces that work on it. One force, anybody knows what force is there? Exactly, gravity. So gravity is pulling that satellite, and slowly it will start pulling it. Everything is pulled by gravity up to a certain range, then, I don't know, becomes minute, so minute. But it's still, at that point, it's still, gravity still has an effect, even though there's no air, but gravity still works. So just if that's the only force that's affecting it, then it will keep pulling it slowly. It will get closer and closer and closer, and the closer it gets, the stronger the gravity. Gravity changes with the change in distance between bodies. The closer they are, the stronger the pull. The further they are apart, the less the pull, as well as the mass of both bodies. But right, so that's why the way to people, if you weigh yourself on top of a mountain, you'll be a little bit lighter because gravity is slightly weaker as you're further away from the center of Earth. But the difference will be so small. But with a satellite anyway, the gravity is there. Now, in order for a satellite again to stay there and not be pulled, there has to be something else pulling it outside. Anybody knows what's pulling that satellite outside? Centrifugal force. So anything that rotates gets this energy to fly away. If you hold a rock on a thread and rotate it and release it, it will fly away from the center. That's natural. So there are natural forces, gravity and centrifugal force. So in fact, the satellite, if it's released, it will fly that way. It's the centrifugal force. And the centrifugal force also changes. The faster you spin, the stronger the pull away. The weaker you spin, the weaker the pull away. Now, we don't want to change the speed. Remember, we want that satellite to rotate exactly one revolution every 24 hours. We don't want it any faster or any slower. So we don't want that change. the speed, and therefore we can't change the speed of the centrifugal force, the pull away. So what we can change is the gravity. So for example, the centrifugal force is this much. We need to have exactly a gravity that pulls, so in such a way that when they are balanced at the end, the satellite, well, that was too much. So usually it's satellite will continue, and from this point it will try fly away, but the gravity will pull it, and the resulting force will be continuing to rotate around Earth exactly at the same distance and at the same speed. So that's the force, the most suitable force we found is at this distance. Remember, if we have a satellite closer here, the gravity will be much stronger. Then you'll need a much stronger pull away force. That means you need to spin around Earth maybe 4 or 5 times a day in order to counteract that gravity. But that is the distance we want that will generate the perfect gravity force to balance that pull away force. And that distance is, anybody knows how far communication satellites are? Are they at 1 kilometer or 30 kilometers or 300 kilometers? Anybody want to have a guess? Or 3,000 kilometers? Which one would probably be more like it?
36,000.
Okay, they're around 36,000 kilometers. 35 kilometer, 700 and some, 60 or something. But we'll say 36,000 kilometers. That is the perfect distance that as it spins, it generates enough pull force, and that equals the gravity force until it stays in the same location. Hopefully, it doesn't move away, it doesn't come closer to Earth, and there's no resistance, so hopefully it just keeps spinning in the same location, and we keep having the dish set at it for maybe 10 years, and hopefully we'll still receive the signal. Right, so that's how the physics of where it's staying and how far. There are other satellites, they're not communication satellites, that they are at much closer distance, and they spin around Earth maybe about 8 or 10 times a day. That's how fast they need to travel in order just to stay at that closer orbit, because gravity is much stronger there. And these are mostly military satellites. Like the military, they have their satellites, send them pictures, goes over an area, take pictures, say, okay, that's the building we're gonna bomb. They send the airplanes, bomb it, and then the airplane 4 hours later comes back, takes picture. Oh, we missed it, send them again, take another picture 4 hours later, yeah, we got it. So that's how the military use it. They can be used for many other reasons. There are weather satellites, there are, all other forms of satellites, but the larger number are those communication satellites that they transmit television signals, telephone communication, music and radio stations and all that. So the only issue with satellites is that they can be expensive. If you want to transmit a signal from here to about maybe 2 kilometers or 10 kilometers or 50 kilometers, it is still cheaper to do it by cable. There is an approximate value, or approximate distance, like if you had flat Earth and it's easy to lay down cables, up to 500 kilometers, still fiber optic cable is better than a satellite. Any longer than 500 kilometers, satellite would be cheaper, even if you want to only send it from one point to another point. So satellites are good for long distances, even if you want one point to one point. Satellite at long distance, it's cheaper, more effective. If you want to broadcast, even at 10 kilometers, a satellite is better. If you want to broadcast to a city, you have the option, you're going to start laying down cables or use satellite. Satellite's quicker and cheap. Like to lay down cables in a city that has no cables, it's going to take maybe, 20 years to make a connection to every house. Maybe 20 years too much, maybe 10 years. But still, you spend a lot of money. Satellite will be a lot cheaper and quicker for broadcast. So broadcasting, generally, that's what satellites are made for and good for. Distances, they're still good for longer distances. Like if I want to send a signal from here to Athens on the other side of Europe, the satellite can be done very quickly and very cheaply. Satellites, are they secure? No, because anything you transmit, everybody gets it in the whole country, on the whole continent. So they're not secure. Do they resist noise? Remember, a satellite is like a radio transmitter, transmits electromagnetic waves. So you send the electromagnetic wave to it, and it sends back an electromagnetic wave that covers bigger area. The electromagnetic wave, once you hear the word radio signal or electromagnetic signal, magnetic, it has magnetism. As long as there's no magnetism in the wave, that's fine. So you might say, sure, it's, satellite coming in the air, there's no magnetism. Wrong. Air is full of magnetism. If we have a storm, the storms, see the lightning strike, that's electricity, that's magnetism. So if there's a storm over your city or over your house, the signal that's coming that has barely small magnetic field in it will pass through a storm that has huge magnetic field, it will be filled with noise. You probably won't even get it. It will be twisted and burnt and increased and everything, that signal. And when you get it, it's not the same signal that was sent by the satellite. So your television screen will go push, push, and then for a few seconds, and then depending on how long that storm stays on top of your house. So satellites are great. In the case of mountains, let's say you want to lay down a cable for 10 kilometers. Fiber optic is always good. But imagine you're going to do it there somewhere in the north of Italy or somewhere near Switzerland and France, Himalayas, mountains, snow. It's, you can hardly walk in there. So it can almost be impossible to lay down any cables or bring equipment to dig cables and tunnels. So satellite will be good even for short distances where normally cables are good. So the environment is also important, or the terrain. They call it the terrain. That means, what does the earth look like, the shape? Is it mountains? Is it valleys? Is it ocean? Sometimes even for short distance, normally satellites are good for long distance and for broadcasting. But sometimes even for short distances, they're good when the terrain is very difficult. Right, maybe we should. So these are the three main parts of the media. Now, what about bandwidth of satellites? They are large, they have large bandwidth, but still not as large as fiber optic. Fiber optic is still the largest. Fiber optics there are now so many bundles, so many cables of fiber optics laying down, connecting different countries and different continents, laying down under the oceans. And they are the main form of communication, the main hub for communication and television transmission and telephone calls and all that happens through fiber optic cables. Satellites are, of course, still there. And remember again, in the old days, how fiber optic became really popular, especially under the ocean, that's when they thought, if a problem happens between, say, Russia here and America here, and America communicates with Europe there, that one nuclear bomb here will blow away all these satellites. They're barely sitting there. They're flying around. You put them out of orbit, and all communication between America and Europe will disappear. So that's when they say, okay, let's have a standby system, and they tried fiber optic cables. But fiber optic cables since then, the first cable was laid down here between Ireland and America back in the 70s, 1976. It was an experimental project, but it's still there, it still works, and it still carries more than 80% of the communication between Europe and America. So fiber optics are really, really great. They last for almost forever. So far, we don't know when, if glass ever goes bad, It might eventually, but it doesn't look like it for now. It's been around for almost 50 years and it works really well. And it has a huge bandwidth. Fiber optic cables are good for, for places like this. Now, how long would a satellite last? Anybody has any idea?
10 years.
Close, yeah. Okay, satellites, I kind of made a wrong statement. I said they will stay and they rotate around forever. There's nothing affecting them. No, in fact, there are many things that affect them. And satellites, as they rotate, usually, usually there's something here flying around Earth as well, maybe slightly further away. How far are satellites from the surface of Earth? 36,000 kilometers. Okay, you were listening. I thought you were dreaming away. Okay. But further away, there's another body, it's the moon. And it can actually have an effect on satellite. It has gravitational force. Everything that has mass has gravity, by the way, just for your information. So the moon also can start pulling things. And also the planets, if they're lining up with the sun, their accumulative pull kind of increases because they all start pulling at the same time in the same direction. So there's so many other reasons. Earth itself is not a really smooth surface. In some places there are mountains and huge rocks, and the mass of some rocks are different to others. And in some other places there's more water that's flowing from one place to another. They all kind of cause Earth gravity maybe to falter a little bit. And therefore, anyway, the ultimate thing is that sometimes satellites are pulled away of their orbit by a tiny bit. And if they're pulled a little bit out, then now the gravity of the Earth, like if they're further away, they're pulled a little bit further away, then their rotational speed, the centrifugal force, starts getting a little bit bigger than the gravity. And it gets bigger, and it spins away and further away, and the gravity gets weaker and weaker, and eventually they disappear. Sometimes the change happens to be inward, closer to Earth. And suddenly gravity is a little bit stronger and starts slowly, over a few years, it will pull them a little bit closer and closer and closer, and eventually they crash into Earth. And they did, it happened to many of them. So what they do with satellites, they put an engine on top of them. With the satellite, they build an engine, a rocket engine. They can't put a car engine because there's no oxygen. They put rocket fuel on it that has its own oxygen, its own burning material, like any rocket. And if the satellite moves out of orbit, they kind of fire a little kind of pulse in that direction and puts it back in the right orbit. And each time it happens, that rocket fires, and they keep and maintain satellites in the right orbit. Eventually, we run out of fuel. So the first few satellites, and when we run out of fuel, then we have no control over satellite. It can start getting closer, it can start getting further, it might stay there for a few more years, we don't know. And in the past, it happened to a few of them that they actually lost control, and they started spinning away and they disappeared. Some of them started spinning closer and they crashed on Earth. And luckily, they've been falling in the ocean. One fell in the Atlantic and one fell in the Indian Ocean. But so if they fall in a city, in a house, they can cause a lot of damage. A satellite is probably as big as a double-decker bus. You know those buses that we ride? About that size. And they need power. They need electric power, and they have, light cells, so they get their power they generated from the sun rays, generally. But the point I'm making, they're very heavy. They're very, they can cause a damage if they fall in a house, or they can cause a lot of damage. They tried to get rid of them, and there are thousands of them that are out of control. Right now, there are thousands, like in the tens of thousands, that are just floating around. And guess what? They're spinning at tremendous speeds, like a few thousand kilometers an hour. They're really moving really fast, and they're real heavy. So if maybe in 10 years, 20 years, you decide, okay, I'm going for a space holiday, and you go in this nice new spaceship, and suddenly, bang, that thing hits you at that speed, it disappears. So it's causing big dangers to all, activities in space, to all other satellites and all other, if people go to the moon or anything like that, they can be dangerous. They don't know what to do with them. So maybe in the future you can come up with a good idea. They thought of many solutions. One of them is to blow them up. So they tried it. They blew a satellite up. So they used to have one big body that's spinning. Now they have a million smaller pieces going exactly at the same speed, and they're more dangerous. So they stopped that. They don't do that anymore. So they're still there. They really don't know what to do with them. This is some of the rubbish that mankind kind of leaves behind everywhere, yeah?
How long does a satellite last?
Okay, how long does satellites? That was the point I was starting with. And I got distracted. When they sent the first few satellites, they were able to put a fuel with them that would last them for about 5 years. So they lasted for 5 years. Now, with the technology and the rocket that can bring even heavier weight, they have enough fuel to last them for about 18 years, 18 to 20 years. So if a new satellite goes out today, it's not going to be there in 20 years. It's not going to be useful or under control in 20 years from now. Maybe they might find a better way of controlling them, and it might increase the lifespan of a satellite. But for now, the difference between a satellite and fiber optic cable from length of time of service, then fiber optic it comes out the top. There's no apparent time limit now for fiber optic cables. Yeah.
What about those with solar panels?
The solar panels generate the electricity enough for the devices, transmitters and receivers to work. That's all. They do not, and the computer to work out the orbit and all that. But they don't have an engine. That doesn't give them an engine to move them left or right. Like if there was air, they probably have fans and they can move it. But there's no air. There's no oxygen there. So no, they need an engine. That power is just for light. Well, they don't need light actually, but for charging the equipment, the transmitters and receivers that are on board.
You said modern satellites last for about 20 years. You said modern satellites last for about 20 years.
Yeah, 18 usually, 18 to 20 years. 20 years probably maximum now. In fact, most textbooks would probably say 16, but they were printed a few years ago, 2 or 3 years ago. Yeah. Yeah, it's very expensive, but from our point of view, we're not in the business of launching satellites and maintaining them. Maintenance is very, very expensive. When they put Hubble, telescope, they fitted in the wrong mirror and they had to fly again to do it. It's just so costly, so difficult to work on. With satellites, there's no maintenance. Maybe, I don't know, maybe eventually they can shoot a laser at it and push it away slowly. I don't know, but somebody will have to come up with some solution or some idea eventually. For now, no, maintenance is not there. But guys, don't mention it as difficult to maintain. It's not our problem. Our problem, if it doesn't work, we go to another company. There's plenty of them right now. For if your company tomorrow needs some transmission and this one doesn't work or their satellite broke down, doesn't matter, leave them, go to another satellite. There'll be plenty of them available. So we're not responsible for, that's not one of our issues. So maintenance, don't compare it to the maintenance of a twisted pair if you want to do it here. It's much easier to do twisted pair maintenance. It's impossible to do the maintenance satellite, but there's better way than maintenance is pick another satellite and use it. So it has no maintenance problem as such for us. Of course, for the owner, they will have a problem. But they probably, they just give it up as well. They made enough money from it. And, yeah?
Whether satellites are moving or not.
I can't hear that one.
Whether satellites are moving along with her?
Again? No.
Satellites are moving along with her? Or
Yeah. They're all rotating at the same speed, rotational speed. See, we are here, right? We are on Earth. We move at 1,000 kilometers an hour. But the satellite here will probably be doing 10,000 kilometers an hour just to stay with us on the same angle. So if I was sitting on Earth now and satellite is there, as I rotate, also satellite spins. It's always in front of me, always. So it's moving, you know, but to us it looks like it's fixed, even though we are moving and the satellite is moving. Okay, it's like you're sitting in a train and a car is driving beside you. The two of you drive at the same speed. You look at the driver is looking at you. You look like you're fixed together, but you're both moving. So the same with satellites. But of course, if you think of the distance they cover, you can work out what's the circle if you had, you know, the distance of from the center. You can actually work out from the center what's the radius of the circle they're on. And you can work out the distance they cover, and then you divide by 24 hours and give you their speed per hour. Maybe that's an assignment. You do it for us. Tomorrow tell us how fast does it actually travel distance-wise. We know rotation-wise, it goes one full circle every 24 hours.
It depends on the radius, right?
Yeah, it depends on the radius, how many kilometers it does. No, but otherwise, this one always rotates one full revolution every 24 hours. And you too, this building is rotating 24, one full revolution every 24 hours. But because it's smaller radius, we are on Earth. I don't know what the radius, anybody knows what the radius of Earth is? I know the circumference is 24,000 kilometers. But anyway, so yes, it is. It's moving with us. It's moving at tremendous speed, even faster than we do distance-wise. But rotation-wise, they call it angular speed. How many angles does it cover? We rotate at the same speed, angular speed.
So is there a range for satellite to be transmitting data? Like it should be.
It's the same distance. There's no attenuation. It's the signal, the transmitter it has is enough to transmit the signal to the surface of the Earth.
Is there a range? Like if satellite goes above the radius which is set, so can it still?
Satellite doesn't change its distance from Earth. It's exactly always at 36.
Yeah, I'm saying what's the minimum distance the satellite can be kept away from the Earth for transmission?
How far it can be away from Earth?
Yeah.
I don't know. They designed the transmitters. They knew it's going to be at 36,000. So they designed transmitters that will send a signal for at least 36,000 kilometers. If it goes out, you must put stronger transmitter. Remember, when we say the attenuation, even for our signal, 100 meters, we can send a signal more than 100 meters, but we have transmitters in every computer. It has certain strength. It doesn't send any more unless there is no resistance. If there's no resistance, the signal will travel. But in satellites, we don't have to worry. They put a transmitter, radio transmitter, that will send the signal all the way to the surface of the Earth and can be received reasonably clear. Okay, let's look at the slides and we cover the. Now, just briefly, which one is better, a satellite or a fiber optic cable? Okay. When would you say a satellite is better, guys? Let's use satellite. Let's not use a cable, fiber or broadcasting. And when would you say, no, we're better off using fiber optic cable? When would you say, don't use satellite, guys, let's use a fiber optic cable? If the distance is short, well, then you say it's a lot cheaper to use fiber optic cable. Any other reason why you might prefer a fiber optic cable?
Well, one reason could be the price.
It could be the cost, yeah. So it's
Cheaper.
cheaper to use fiber optic cable, is it?
Yes.
Always. Let's let me finish with this So you are saying fiber optic cables are always cheaper than satellite. Good answer, that's the wrong answer. Are satellites cheaper or more expensive than fiber optic cables? Which one is more expensive, fiber optic cable or satellite to use? A satellite. That's exactly what he said. What do you think? It's wrong answer.
Fiber optic satellite.
Yeah.
Depends on how far you're going and what the
Yeah.
terrain is.
It depends on so many factors. One of them, and then one of them is the distance. If you have a distance of 5,000 kilometers, satellite is much cheaper than a fiber optic cable. Are you listening to me? If you have a distance of 5,000 kilometers or 2,000 kilometers, it's cheaper to use satellite. Yeah, it's cheaper to use a satellite. Only 500 kilometers or less, maybe fiber optic can be cheaper, okay? So for short distances, maybe fiber optic is cheaper. Long distances, satellite is cheaper. What about point-to-point transmission? We're going to send signal from one point to another point. Shall we use a satellite or a fiber optic cable?
It depends if it's short distance, then we'll use.
Very good. It still depends. If it's a short distance, then definitely fiber optic. If the distance is long, even though satellites are not point to point, they're normally, by their nature, they are broadcast device, but it's still cheaper and better to use it than to use a satellite. Well, sometimes even if the distance is only 20 kilometers, it would still be better to use satellites. When? Well, why would you still insist on a satellite? I say I have to deliver data only about 30 kilometers. Shall I use a satellite or fiber optic?
It just goes one way.
Now hold on. No. And you might still say, no, we can't use fiber optic cable. We need to use satellite. When? Any idea? Pardon? Yeah, if we're in a great hurry, if we're in a great hurry, tomorrow you can start transmitting. So this is called setup time. If you're in a hurry to do let's say there'll be a big, music festival somewhere in some city. Well, no, in some open area. There's no communication, there's nothing. You say, all right, we can go and build a network. Yeah, this will take you a few years or a few months to build a network. If you need to do it next week, satellite is a better way. What else? What other reasons why you might say a satellite is better than a cable, even if the distance is short? Anybody has any idea?
It's like mountains.
If the terrain is difficult to lay down cables or impossible, then even if the distance is short, and that was the question, you might say, no, we're better off going for a satellite. Did you hear that? The terrain? Terrain. You know what the terrain is? Mountains, maybe snow, maybe difficult to use. So let's look at these slides. Okay, there are cables. They are of many different types of cables, but we'll only be looking at two of them. There's a cable called twisted pair cables. This is the most common now for local area networks, and it has been the last few years. Up maybe the last 20 years. Twisted pair is the one that's in use. But now, slowly, they're moving towards fiber optic cable. It's too expensive, but it's becoming cheaper and cheaper to use at home. And the good reason why we should use it, why should we change our fiber optic in a local network from twisted to a fiber optic? Why? Anybody has a good reason? Why do you think fiber optic can be better even for local area networks than twisted pair? You know the twisted pair, the two wires, electric cables or fiber or light cables, the fiber optic cables. Any idea? Okay, well, if we are in a kind of this environment, hopefully there isn't a lot of humidity, there's no salt in the air, and therefore twisted pair will last as well. It'll probably last for 10 years, but we can replace it. It's not That's huge difference. Anybody else you might want fiber optic instead of twisted pair? Huh? All right, I have two people.
Because of the heat. There is no radiation.
Low radiation. Okay, if security was not really a major issue of ours. Good, yeah. More data, yeah. But it has, fiber optic has a very huge bandwidth. It can transmit a lot more data. If our network, becomes really slow due to, we can't, if we are exchanging a lot of information, especially like videos. If our organization is video production kind of thing, everybody's working with videos, sending parts of videos to everyone else. So there's a huge amount of data that needs to be transferred fast. Fiber optic are much, much better because they can deliver not faster, the signal doesn't go much faster, but you can bring more signal at the same time. And therefore, overall, you can say it's really faster because you're delivering more at the same time. But it's not really higher in speeds. It is slightly higher, but that's not the major advantage. The major advantage, the bandwidth, the amount that you can carry, that's the same speed, while the twisted pair, just like one wire, imagine instead of having one twisted pair, you have 1,000 twisted pairs. They can all carry different capacity. So it's much bigger capacity. Anyway, the other cable is called coaxial cable. It's no longer in use in any communication networks, in a common place. Coaxial cable, just like the antenna cable for televisions. I don't know if you've ever seen an antenna cable. I'll show it to you, but you don't have to worry about it. I will not be asking you about coaxial cables. The two cables that are in use and you need to know about them is the twisted pair or the fiber optic cable. One is an electrical one. And the twisted pair is just a pair of cables. That's why they call them pair. They're two wires. They're, hopefully both ends they'll form an electric circuit. And they are twisted. And that's why they're also called twisted pair. They don't live in straight lines. Because when they are twisted, they will not take a lot of noise from electromagnetic waves. Because a wire that takes a lot of noise is like an antenna. A radio antenna is a straight wire. It receives the signal from, takes the electromagnetic wave, passes through the wire, generates an electric signal in it. But if it's twisted, like your radio antenna or television antenna, if it's twisted and broken, it will not be a good antenna. That's why they twist this. And they run, see the bandwidth goes up to 100 megabits per second. And they're getting better as well, the twisted pair. And so if you had just two straight wires, and if you had a noise source, a machine that has magnetic like air conditioning unit beside the cables, and if one of the wires is closer than the other, then it will have more noise in this wire than noise in this wire because it's closer. And then it's difficult to deal with if you have different levels of noise on the same electric circuit. Sometimes you can filter it out, but if they are already at the same level. So it's like if you turn the volume down, the noise drops. But if one noise in one end is more than the other, it makes it difficult to deal with. So that's why they twist them. So they twist them for two reasons. Twist them to make sure that they're not good conductors, so they don't receive, or they're not good receivers, or they're not good antennas. And the other reason is to have, if we do have to have noise, we better have it on both wires equally. It's better than having one of the wires huge amount of noise and the other one less amount. So it's better to twist those. Anyway, and when you buy them, normally you'll buy them in a group of bundles of pairs, normally 4 pairs of wires. If you go to a computer shop now and say, can I have a network cable? They most likely will sell you one that has 4 pairs of wires inside of it, and they are colored in a particular coloring scheme for many different reasons. They're standard, the colors are standardized, but also for you. So when you connect the green cable on this side, you go to the other end, you don't connect the wrong wire. So you'll be, working on the same wire from both ends of the cable. And this is really what they look like when you buy them off the shop. This is about 3 years ago. This is class 5, I think. The wires every few years, 5 to 10 years, they improve them. They make them a little bit better. The first pair of wires they used, they only had an attenuation rate of 10 meters. That's all. After 10 meters, you need a repeater. So they change the material in there. It's mostly copper, but they put 1 or 2% of other metals, mix it with it, and it improves, the resistance and the flexibility and all that. So as they improve it, the distance increases. We get better attenuation. So right now, the attenuation, they've reached class 6 or 7. Right now, they're at class 7. But class 6 is 100 meters. I think class 7 is also 100 meters, is the attenuation rate. But, and when you go to buy from the shop, maybe you won't get the old ones. Class 1, 2, and 3, and 4 are gone. You might get class 5 or class 6. Class 7 is still a bit more expensive. But they're reasonably cheap. They probably cost 20 cents a meter. Class 5, maybe a little bit more expensive, class 6 and 7. And the terminal looks like this, the plug that goes at the end, and it's squeezed onto it, and it takes all the 8 wires, and they need to be lined up in a certain way, depending, are you connecting a computer to a computer? But that's not what we normally do. We normally connect a switch to a computer. Like now, to see, when you build a network, you bring a device, we call it a switch right now, the most common device now. And maybe it can take 4 machines, or 8 or 16 or 32, or even more, 52, 64 machines, and each one of them is connected by wire that has a standard plug like this. Hopefully we'll try and get manufactured network cables if we can, if we get the cables on time. So these are what the wires look like. These are the exact colors that you'd expect to find. Some of these wires will have an extra metallic cover onto them. And they're known as shielded cables. So these wires, the standard ones, they radiate. And they also, if there is magnetic field in the air, it will generate noise in them, small current that we call noise. But the shielded ones, they try to limit the radiation. So if the wires inside radiate, they kind of absorb most of it and hold onto it because it's a metal, so less radiation goes out. And if there was noise, there's magnetic noise from outside, it will have less effect on the wires. So they're slightly better, but they are not fully 100% isolated or safe. They still radiate a little bit. And they're more expensive, and they are known as the shielded twisted pair. So twisted pair can be shielded or unshielded. The normal standard ones that you buy are known as the unshielded. This is number 6, I think. This is category, this is category 6. In category 6, they also, I don't know if it makes any difference. I'm not, into manufacturing cables, but they have a plastic kind of separator, like this. So every pair go separate, they don't interact a lot. But that plastic is not a good insulator or anything. I don't know why they do it, but it must have a good reason. But it's not that much of a difference between category 5, that's category 5, and that's category 6 cables. They're fairly similar, but category 6, they have that extra cable. But they say these wires, they can deliver higher speeds. They can deliver higher speeds than that one there. And they're slightly more expensive as well. But that's the plastic separator that's in there. So you need to know those twisted pair cables. This is a bit of information about them. Right now, there's category 7 is coming out, but this is how much data they can. The cost, obviously, number 5 is the cheapest, 6A is the most expensive, and this is how much data, or how much, that's the speeds, or how much they can deliver. every second they can deliver 10 gigabytes. What's a giga? A giga is 1,000 mega, it's a billion. Like everything goes in, you should maybe get those terminologies. What's a byte, a kilobyte, a megabyte? Kilobyte is 1,000 bytes, megabyte is 1,000,000 bytes, gigabyte is 1,000. So every word will add another three more zeros. 1,000 bytes, that's 1,000 million, that's a giga. Okay, so with 3 zeros, it's kilo. 3 more zeros, that's a million, mega. Another 3 zeros, different countries, they might have different words for them. But billions, they refer to them as gigabyte. So that's as much data as they can deliver. Right, this is the coaxial cable. You can ignore it, but I'll just show you what it looks like. It's like the TV antenna, old televisions. They used to have an antenna cable like this. It looks like it. And then computers started using this up until the year, maybe, you know, the 90s. By the year 2000, probably you don't find them in the shops, unless if you look for them. But in the 80s and 90s, there used to be all network cables. Local area networks are powered by those connected by coaxial cables. They're better actually than the twisted pair in as far as the speed and the attenuation. But still, they changed to twisted pair because it's a lot cheaper. Now we're talking about the fiber optic cable. This is the cable that's made up of glass. And that's, let me just show you what it looks like if it's still there. Is the image there? No, it's not there. Sorry. Yeah, at last. So that's what the fiber, it's like slightly thicker than the hair, the few hairs put together, human hair. It's a hair of glass, made of glass. And because it breaks so easy, they put pure plastic, mix it with it when it, you know, when it's being manufactured. So it has a bit of flexibility, but not very flexible. And when they make one, they make a big bundle of them. Each one of them is like 1,000 twisted pairs. So, and they put, you know, a bundle of those into one cable. So when you buy a cable like this, but usually you don't buy a cable like that, you buy one wire. But if a company, when they lay down a cable in any city, under the ground or under the ocean, they never put one little glass wire. They put a bundle or big bundle of it. So, you know, you don't have to go down again and reinstall again every time you want to add. And this should be enough to power a city, like to all the communication in one city. But remember, once that breaks, you can never weld it in situ. It doesn't work. But if you want to tap it, you cannot do it. If you want to make an extra connection, another wire coming out of it, you can do it with twisted pair, but not with fiber optic cables. So they generated these. They started manufacturing these. And these are like multiplexers. So you plug that into one wire, and they spread the signal inside maybe glasses and lenses. So it's all light kind of operation. I'll go back. Don't need to worry about, there's some calculation here that we don't really need to worry about, but you need to know that you start with electric signal, like your computer has an electric signal. First it's transferred into light through a small machine that takes electricity, generates light, like a torch that takes battery power and generates light, but it's like a laser. And that laser shoots that light signal into the glass wire, and it keeps, if it tries to get out of it, it will be reflected back in. It will be floating from one end or one edge to the other edge until it reaches the other end, and the other end, it has a device that's sensitive to light. Once it gets light, it generates electricity. So you start with the electric signal out there, only during transmission we change it into light, and it keeps hitting the edges and reflecting inward until it gets to the other end. It travels at the speed of light, which is faster than electricity flowing, the electrons flowing through a wire. Maybe 2/3 1/3 faster, this one. So the electrons also travel pretty fast. They travel at the 2 speeds or the 2/3 speed of light. And the angle that it hits the glass, it has to be at a certain angle, or else the light will go out of the glass. And they call that either reflection or refraction. If it's reflected, it stays within the same medium. If it's refracted, it goes out to the other side. So the angle has to be, we don't want anything coming through the glass, we don't want it to exit, and therefore the angle has to be reasonably, going in with the line of the glass. Don't hit it on the sides, it will not travel through it, it will get out. So that's really the maximum angle, or in this case, so this light beam, if it goes any higher, so if the angle, if it comes down, then that's the normal. And usually that's it, you line it up and there it is, it has to go this way. Don't shoot it this way at an angle that it might exit the hair, rather than, it might refract from the hair rather than reflect into it. Reflection is staying in the same medium. Right, so you don't have to worry about the calculations that's done in there. But these are some of the advantages of twisted pair. The problem with fiber optic is that you can barely put the laser towards one end, you can't also receive the light in the same one, or else you have to be changing sources and the gun with the sensitive cell. So they don't change. You use one glass, you use it either in this direction or this direction all the time. You stick a laser on one end and a light sensitive at the other end, and so they call that simplex. Fiber optic is a simplex communication medium. Twisted pair, you can send electric signal in both directions, or you can send data in both directions. You send this way, and the opposite side can also transmit a signal in the opposite direction. So twisted pair are the easiest to work with. Everybody has worked with twisted pair. Twisted pair has been around for over 160 years. The telephone companies used to use twisted pair, and they still use it, and then computers started using it, and they still use it. Yeah?
Yeah, in twisted pair, doesn't the radiation from one pair affect the other?
Yeah, in twisted pair, because it radiates. And you have 2 wires, 2 pairs, and another 2 pairs beside them. So if one radiates, it will generate a magnetic field that will affect the other one, that causes noise in the other one. It happens. And in the old telephone systems, sometimes you pick up the phone and you can hear 2 people talking, another 2 call, and that's coming from this radiation. So another phone call in 2 pairs, and your wires are close to that, so they generate magnetic field and they generate noise. And that noise is exactly the call that they were talking. So it's actually the call used to go from one to the other. So they started installing filters in those and remove those extra calls. But yeah, that's one of the problems with twisted pair. They generate magnetic field, and if there is another pair of wire in the area, which normally you would have lots of wires going together, that call will be picked up by all the other wires. But in the telephone companies, they sorted that. They have special filters that will eliminate that. But that problem is there. And if you do it, and if you have a pair of wires or multiple pair of wires in your, like office, then one of them will actually cause noise to the other one. And you don't have the special filter, so it's going to be difficult.
No, I mean, you said that in one single pair we have 4 pairs, right? So in one cable we have 4 pairs.
You have what?
We have
1 pair. Oh,
like,
4 pairs.
Yeah, inside one cable we have 4 pairs, right?
Yeah.
So doesn't that affect?
They do, yeah, they do. That's exactly the same as with telephones where you'd have more of them. Normally here, with the 4 pairs, they're used for different reasons, but we don't use the 4 of them. When we set up a local area network, we only use 2 of those wires. So computers are used to Like we'll talk about connectivity later on when we connect computers, so we'll leave that to that time. So wires are easy to tap, twisted pair wires, and they're easy to twist into tight corners. So if you want to bend them around, they're easy to bend rather than twist, and they're full duplex. What's a full duplex communication? Anybody, do you know what full duplex is? Communication, you can send and receive information at the same time. That's called full duplex. Simplex, that means you can only send in one direction, never in the opposite direction. Duplex has two types: full, that you can send and receive at the same time, or half duplex. You can send and receive, but not at the same time. Send, wait, receive, wait, send, and so on. So either send or receive, but not at the same time. So twisted pair, you can actually send one signal this way and the other guy sending on the same wire signal in the opposite direction. As long as they are of different frequencies, they will work perfect. And meter for meter, twisted pair is cheaper. So you can only say it's cheaper if you say, to go and buy from a shop, give me 2 meters twisted pair, it'll be cheaper than 2 meters of fiber optic. But remember, what you get from twisted pair can carry very little. Those fiber optics can carry a lot more than maybe 100 or 200 of those cables are. And not fragile because the ones that are made of glass, the fiber optic, are very fragile. So this one, you can walk in it, it's no problem. With the fiber optic, you walk in it, you can break it. But twisted pair has lots of problems. And here they are. This note is on Moodle, so you don't have to write it all. But it's not secure for 2 reasons. You know what? Give me one of those reasons. Why twisted pair is not secure?
It radiates.
It radiates. Why is twisted pair not secure?
Oh, you saw the answers.
Oh yeah, I know you already saw them. Give me the answers.
It is easy to tap.
Yeah, thank you. It's easy to tap. So it's not secure for 2 reasons. First, it radiates. Any message you put it in twisted pair, it's generating magnetic field. Anybody can pick it up. It's like you send a message with somebody, a friend of yours, and you tell them, listen, don't tell them that. And he walks up and he's saying the message all the time until he gets there. Everybody hears the message. That's what twisted pair does. It talks all the time. It radiates. And it's also not secure because anybody can connect their wires to that twisted pair wire anywhere, easy, and they can connect their computer and they can pick that information. So they can pick the information either by touching it, that's called tapping, or without touching it, picking the information with wireless receivers. And it has very low bandwidth compared with fiber optics, and it rusts quickly. If you put it in salty environment or humidity, it will rust away or corrode. And it's much shorter distance. The attenuation is about 100 meters, prone to be affected by electromagnetic noise, so it can suffer from noise. Apart from security, it's also can be very noisy. Low bandwidth, that's already mentioned, and heavier in weight. If you have to get maybe 1 kilometer of twisted pair, you probably need a big truck to carry it. Fiber optic, it's not that heavy because of the weight. Fiber optic has greater bandwidth, is more secure for 2 reasons. It doesn't radiate and it doesn't take noise, and it's difficult to tap, and it doesn't get affected by electromagnetic noise, and it does not suffer from attenuation as much. Okay, it suffers. What's the attenuation on fiber optic cables? Any idea? How far would you need a repeater for a fiber optic cable? 20 meters? 200 meters? 2,000 meters? What's a fiber optic cable? When do you need a repeater? What about twisted pair? How frequently do you need a twisted pair? 100 meters. Every 100 meters you need a repeater. For a fiber optic cable, what is the distance where the signal is no longer recognizable and you need a repeater? 100 meters. Or kilometers. 60 to 100 kilometers. Okay. The problems with fiber optic cable, it's simplex. You know what simplex means? Only in one direction only. Every fiber optic wire. So if you need to talk both directions, you need two wires. One in this direction, one in this direction. Cannot be tapped, so that's secure. It's fragile. It breaks easily and difficult to bend around corners and higher cost for the same length of cable, but it might work out cheaper if you have large amount of data. Be careful. It's point-to-point medium. It's like all cables. They are point-to-point. They're not broadcasting, and they're not suitable for very costly or difficult terrain. So if the environment is very difficult, not suitable, even if the distance is short. But they're suitable. They are. You need to know that they are the ones who are carrying most of the communication. They're under the oceans. The oceans are not full of them, but there's lots of fiber optic cables running under the ocean. And these are the approximate distances. Right, this information is just general information that there are different frequencies of radio transmissions. They use different frequencies used by different devices and different technologies. Radio communication uses certain frequencies from 3,000 hertz to 300 million or billion hertz. Gigahertz it's called. That's really how radio transmitters work normally on Earth. This one sends it, the receiver and a sender, receiver and a sender, and you distribute it around Earth. We don't need to worry about radio transmission. The next one is satellites, how satellites are operate. These are the communication satellites we just talked about. They rotate around Earth, and they're about 22,000 miles or 36 or 37,000 kilometers from the surface of Earth. You can be point to point if you want. This guy can send a signal and the satellite transmits it, this one can get it, but also somebody here and there, so it's a broadcast. But if you want to use it for point to point, that's fine. It's used for oceans, like the Atlantic Ocean. There are many satellites that do communication, but also there are many cables that connect Ireland or other countries with America, from Europe and America together, between America and Europe. France is also connected to South America and North America. Usually you get maybe television stations that transmit a signal and you can receive it directly, or it can be received by another receiver that spreads the TV signal to multiple houses instead of, you can have your own dish, but there can be one dish in the area and then you're connected with wires to that dish. So satellite signal can come to one location in the area and spread to that area by cables. Or it can be like in a local area network. Many local area networks, they have a dish, a receiver, and they receive from a satellite, and you're connected to the world. Signals from fiber optic cables, they can be affected by storms, electric storms. They will cause noise. So the signal coming from a satellite is not pure. It can contain noise, can be destroyed. This is another image of how far, and it's always at the equator. And there are plenty of those satellites. There are loads of them. So wherever you are located, anywhere in the world, remember, if you're on the north side of the hemisphere, all satellites will be southward to you because they're all at the equator. Like we are here, the equator is, we have to look south to see the equator. So all the satellites will, for us, our dishes need to be pointing to the south, but south a little bit to the east or west, depending on which satellite you want to point at. And if we were in the south, if we were in South Africa, for example, we'll be looking north towards the satellite, but north with a bit of east or west to pick which satellite you want. All these are at the equator. So depending where you are on Earth, you'll be pointing the dish. And you may not be able to see all the satellites. For example, you're here in Europe, and these satellites on top of Europe, you can see them, but you can't see the ones on the opposite side of Earth. So your transmission and reception can only be to those satellites. And this is just shows the idea that that satellite is fixed towards Earth. It's rotating at exactly the same rotational speed as Earth. So to somebody on Earth looking at that satellite, it looks fixed. When the satellite is not fixed, and the person is not fixed either. Everybody is moving, but the two of them are locked together. That's why you put your dish on one satellite, it'll always be pointing at it. Unless, of course, the satellite moves out of orbit. It can be point to point, and this just indicates the forces that affect the satellite. That's gravity and centrifugal. The further away from Earth, the gravity is smaller. The closer to Earth, the gravity is stronger, and you need to have stronger centrifugal force to balance it. And therefore, a satellite closer to Earth must rotate much faster, must go around Earth a few times a day, not once, like the communication satellite. But these are the military satellites and spy satellites and things like that. They rotate around Earth maybe about 10 times a day. So you can imagine the speeds they go at. Satellites' advantages, they are cheaper for broadcasting. So anytime you want to broadcast, cheaper to use satellites. Broadcast to a city or a town, or a continent, a country, a full country. Cheaper for very long distances as well. Anything more than 500 kilometers gets too expensive with cables. So satellite becomes cheaper. It covers very large area and quickest to set up. You want something done next week? Satellite is your only way. More suited for difficult terrain. So even if the distance is short, still maybe in some areas of the world, you cannot actually go and dig. But they have problems. They are not secure because they broadcast. They are affected by electromagnetic noise if there's electric storms in the area, affected by storms and rain, and they have a delay of 1/4 of a second. And that's because the distance, because every signal has to travel up and down. That's a total of 72,000 kilometers. 72,000 kilometers. The speed of light is approximately 300,000 kilometers every second. 72 is about 1/4 of that distance, and therefore it takes 1/4 of a second. So every satellite signal has a 1/4 of a second delay. Sometimes some people, they call the television a live show on the TV. The TV goes through satellite, it comes back to them. So you're watching yourself. For example, I pick up the phone and dial RTE here, the radio station, the television station. My signal goes through wires to the station, goes very fast. I'd be talking to them. And when I look at myself in the television, the signal goes up and back, and it's 1/4 of a second later. So I talk, and then I can hear myself talking afterwards, like an echo. Some people can't do that. Some people actually get mixed up when they speak, and then the timing goes out. So most of the time, the TV station, they tell you, switch the television off. Don't talk and look at it. Because it kind of wakes you up. There's a delay. So that delay is, sometimes it's an issue, but it's not a big issue in most cases. But sometimes it's very important, quarter of a second. In some systems, maybe we cannot put up with. So it's just good to know. If your system doesn't care about quarter of a second, then satellite is good. But if it can cause a problem, well, then you can take it into consideration. And that's really the end of media. Right, what time is it now? Oh, we won't start something new. So just a quick question. Now we've seen satellites and cables. I always ask you, which one is better, twisted pair or fiber optic? No, I'm going to ask you, which one is better, fiber optic or a satellite? What do you think? Thank you, yes. Now, you tell me, depends on what? Give me one reason where you say, no, satellite is better than a fiber optic. When? What's the distance, right? When is it good, like, to use satellite? Long, right, so if the distance is long, use satellite. How long is a good distance before you can say, no, let's use twisted pair? About 500 kilometers, 500. Right, give me another reason why satellites are better or worse. If we want to broadcast, then we better use a satellite, not a cable. What if our broadcast is secure, so we don't want anybody listening to it? Would you still recommend a satellite?
No,
right, but sometimes fiber optic is not available, and for security, you'll have to maybe encrypt your transmission, and the receiver has to decrypt it. You need to take extra precaution. If any medium is not secure, then you should take precaution. In fact, always assume that the medium is not secure. When it comes to security, always assume and take precautions. Any message you want to send, encrypt it and send it. Whether you satellite, twisted pair, or fiber optic. Always assume, even along the trip, maybe it will change from, like you send a message from here to somebody in, say, Athens. It might go through wire and then satellite and then twisted pair somewhere, so you go into multiple media. You're not always guaranteed it's going to use the same medium. Okay.